Testing. 1, 2, 3, testing. Okay, today we're going to follow up on some more important problems, historical problems, in addition to some things that you might choose to do your final project on. Before we get into that, I'd like to just show you also some links on Unsolved Problems. I've been rapidly getting new URLs towards the bottom of a good list of problems that, I mean, these are major problems worth $1 million if you solve them, like Fromage Test Theorem and stuff, but there is a list of these last 3 links here. I got a list of these 17 problems, some of which we've seen before, the Goldbach conjecture. There's a number of these very hard problems, and a link back to the Clay Math 7 problems of the millennia. This is a nice link to just a general list of collections of math problems. So if you want problems in algebraic topology or various individuals problems, open problems on discrete and computational geometry, open problems in topology, etc. So you can generally look through those for problems that are open. And this I found is a site of open problems at the undergraduate level, including an interesting link to Venn diagrams. I didn't realize there were open problems in Venn diagrams. So you can go ahead and look here. This is a Venn diagram with 4 closed curve ellipses, and then they have a statement here. It's possible to create a Venn diagram with 5 triangles, but it's very tricky. Open problem is, can you create a Venn diagram with 6 triangles? The largest Venn diagram that can be created with ellipses has 5 ellipses, one discovered only recently. And then they actually have some other open conjectures on Venn diagrams. So there's also graph theory, combinatorial geometry, and number theory. So I just bring that to your attention of problems that are basically formulated at the undergraduate mathematics level, in case you ever are teaching AP classes and your students come in wondering what kinds of stuff is there to do as a mathematician. Okay, back to our lecture. These are considerably more challenging problems, and I'd like to just recall that in the previous lecture, 19, I had 10 historically important problems. The first one was factoring primes and relating that to what's called the RSA encryption algorithm, and I gave a starting point for that. There's a classic recent problem in chaos and dynamical systems. In fact, there's a very much of an open problem that was just recently solved regarding the Lorentz attractor, whether it was a strange attractor or not. I always assumed that it was known that it was, but it was just proven recently that it was. Geometry, there's a lot of open problems in geometry, and this particular one, it just relates a classical discipline of mathematics, projective geometry, and how it relates to a branch of computer science, surface representations, and also graphics. Algorithmic complexity, Karmakar's algorithm has attracted a lot of interest about 15 years ago as an alternative to the simplex algorithm. Infinitesimals, this is a very early development, kind of fell out of favor and then was resurrected about 20 years ago as non-standard analysis and transfinite numbers. There's also non-Euclidean geometry. It's become very popular as a way of defining non-standard, non-Euclidean, non-Cartesian metrics on data sets. For example, you can apply a notion of distance in databases, or graphs, and you can apply some nonlinear geometric ideas to data and data mining. A very classical problem that was present back in Newton's day was the n-body problem. Once Newton formulated the notion of gravitational attraction between bodies, or it could be electrostatic, how to solve in general the problems for stable systems of n greater than 2 bodies. After all, our universes are fairly stable, and it's actually an open issue about the stability of n-body systems. the solvability or non-solvability of polynomial equations, fractals and fractional dimensions, and there's a very nice little foray you can make in what's known as Feigenbaum's universal constants, and I gave a starting point. Of course, there's the big open problem of the last 2 centuries. I was reading that Fromage's last theorem has the distinction of being the theorem with the most incorrect published proofs. And between like a 10-year period between 1908 and 18, there were over 1,000 incorrect proofs of Fromage's last theorem published. So I don't necessarily make a career out of publishing incorrect proofs, but that's an indication of the difficulty. So today's lecture, I wanted to just branch off. So Fromage's last theorem does have the distinction of being the theorem with the most incorrect proof. Ranking right up there with Fromage's theorem is the Riemann hypothesis. Now, the Riemann hypothesis has to do with this series 1 over n to the z, or 1 over n to the s, the zeta function. So this is a complex function. It was defined as over the reals and then by complex extension. So for example, when s equals 2, the sum of the reciprocal squares is pi squared over 6. Zeta of 1, in fact, does not converge, right, because you have the geometric series, or no, the harmonic series 1 over n to the s when s equals 1 is 1 over n, and that diverges logarithmically. So there is a relationship between the prime numbers in this series. In fact, I think there's a link shortly down here. If not here, it's in the next link in this, where Euler discovered a very fascinating result that if you take the products, this product here, 1 over p, the product of 1 over 1 minus the prime to the minus s, has this identity, namely the inverse powers is related to the product. So these are actually related to the roots. So the prime numbers appear as roots of this over on the right, and this becomes the zeta function as a sum. So you have the infinite sum of all the integers to reciprocal powers, and then a set of infinite products that runs over the prime. So if you look at the graph of this, and that's actually the previous link here. If you look at the graph of this in the complex plane, for the value s equals 1/2 plus b times the integer, so if you let zeta of z run over complex numbers whose real part is 1/2, you can see that zeta actually has zeros at certain values where the real number is 1/2. If you put in a third, there are no zeros. So the conjecture was that zetas, all the interesting zeros of zeta, have real part equal to 1/2. So that is, all the zeros lie on a line of real part zeta equals 1/2. So as of May 4th, it has been known that the first 10 billion zeros have real part equal to 1/2. So that might lead you to conjecture that they all do, but of course that's not a proof. And the proof of the Riemann hypothesis is actually still unknown. No one has proved it. There are some links of almost proofs, and there's, I guess, at least one person that's claimed that they proved the Riemann hypothesis, but they keep getting sort of shot down. So the Riemann hypothesis, again, not that you have to prove this for the class, but the idea is to summarize the history of this, explain why it's important, and the kinds of interesting mathematical problems that have been generated by people attacking this particular problem. So next to Fromage's last theorem, this is probably the number 2 open problem of the last 100 years. This is not exactly an open problem, but it's related to the previous problem of factorization of composites into large primes. If you're going to factor numbers, you have to have a list of primes or be able to determine whether a factor is a prime or not. And a sort of twist on this is the fact of how do you generate large primes, because the RSA and other encryption algorithms need large, say 512-digit primes. Now there are actually theorems that relate to how many primes are in certain intervals, and if you look at 10 to the 512 or 2 to the 512, yeah, here we go. There are approximately 10 raised to the power 151, that's more than a Google, primes which have 512 bits or less. So if you're looking for a 512-bit binary bit prime, then you have quite a large number, 10 to the 151. And the odds at picking a prime at random and making it the same as someone else is, of course, 1 over that. So that's why people are fairly confident that these cryptography algorithms are fairly stable, because picking a prime at random with 512 binary digits is fairly small. Not exactly. I think this is a typo. I think there are more than 1,077 atoms in the universe. I think there's probably 10 raised to the 77 atoms or something, unless I'm mistaken. Yeah, so there's a 10 to that. There's a soup HTML there. Now, if you go down here, it actually gives an algorithm for generating prime numbers. Actually, you don't generate a prime, but you choose a number which you can determine if it's a prime or not. So there are tests that will tell you whether a number is a prime or not a prime without actually factoring it, which is a very expensive way to determine whether it's factoring. So the idea of this prime number generation, and this is one of the recent tests, the Riemann-Miller test, it says pick a number at random to check, and then calculate the residue b, where b is the number of times 2 divides p minus 1. So p minus 1 is equal to 2 to the b times m. So m is, b is the exponent, so it's the number of times 2 can be factored into or appears as a factor. So you've got this number b, and then you choose another random number that's less than p, and then go through this step here. And then finally, the conclusion is, if any of these cases are true, if this j is greater than 0 and z equals 1, where j and z are from this steps 3 and 4, then p is not prime. If it satisfies step number 5, it may be a prime, and if it satisfies step 6, then it's not a prime. So you can basically rule out things which are definitely not primes by this test. So it's a very fast test of determining whether a number is not a prime. If it fails those tests, then it's in a collection of possible primes. Now the odds of a composite number passing these tests decreases pretty quickly, and in fact you can refine the test and actually come up with confidence intervals. There's a refinement called Fromage Test that says if p is a prime, then 2 to the p mod p is 2. So if you put in a number p and 2 to the p mod p is not 2, then you can guarantee that it's not a prime. But if it's equal to 2, then it's the converse, and you can't conclude that it is a prime, but you definitely know if the test fails that it's not a prime. So that's an additional level of filtering, and then it gives you some practical considerations on how to choose. Now there's something called a strong prime. See if it goes in, indicates, yeah. So a strong prime has to do with numbers p and q and p plus 1 and p minus 1, and you can do a little bit of reading, but the strong primes are basically there to act as to sort of thwart some of the older prime factorization schemes. However, it makes a note in this document that the best factoring algorithms now basically doesn't matter if they're strong primes or not candidates. Now, there is a link. It was said in here that this is a simplified version of the prime generation algorithm that's actually used, which is the so-called digital security DSS algorithm. Now, this is the NIST. Now, NIST is what was formerly called the National Bureau of Standards, NBS. This is the National Institute for Science and Standards and Technology, NIST. And this actually gives the complete mathematical algorithm for generating primes for use in the encryption algorithms. And it actually goes through the DSS and the DSA algorithm and all its parameters. So if you really want to know what is it that people are really using, and this is a mathematical statement, proof and lemmas, that the DSS algorithm works. Another very famous one, which I'm sure all of you have heard, is the four-color theorem. Now, this is not an open problem. This has been proved. It's one of the new brand of theorems that was proved sort of by exhaustion using computers. But the basis says that you can take any complicated map you want and color in the states or the countries, and no two of them will be adjacent with the same color. So this goes through the sort of history and the proof, etc. And these are sort of the kinds of things that you have to enumerate and go through to guarantee that all possible cases of a map can be colored with 4 colors or less. A problem that was of interest to me some time ago is Mark Katz's question, and this was formulated back, I think, in the 70s, late 60s or 70s, 1966. At that point, there was the following question, and this has to do with what are called eigenvalues and eigenmodes. If you take a two-dimensional drum and stretch it, take a curve in 2 dimensions, turn it into a drum and hit it. If you look at the Fourier coefficients, the eigenvalues, the sines and cosines, the modes, it will have a sequence of real eigenvalues because it turns out that the differential equation is self-adjoint, so you have a real symmetric, there's no imaginary component. The question is if you take 2 different drums, do they generate the same eigenfrequencies? And for a very long time, it was thought that the answer was no. That is, there was almost a one-to-one correspondence between the eigenfrequencies, the acoustic frequencies, and the geometrical properties of the object. And so Mark Katz formulated the conjecture that each object, or each two-dimensional drum head, if you will, even if it had holes and other things in it, generated a unique set of spectra. And that was later turned out to be false. So there's a link. This is a rather long article. It was actually, part of the conjecture was that he proved that you can hear the area of a drum. That is, the asymptotic distribution of the eigenvalues told you things like the area, which is just the integral, the first moment, which had to do with the perimeter of it, another invariant, which had to do with the number of holes. You could tell that from the asymptotics of the spectrum. But it turns out that you cannot, in fact, and there was a counter example to this, which is in the open Unsolved Problems, or let's see, let's see, where is that? It turns out that you can't always hear the shape of a drum, and this is a very fascinating problem because some people actually showed that in high enough dimensions it was false. For example, in '64, the very famous mathematician John Milnor found 2 16-dimensional manifolds with the same spectrum. But for 2 dimensions, it wasn't until 1991 whenever these guys actually constructed. These are 2 regions that have the same spectrum, and they obviously look different. I believe these are 2 of the authors of it. So here there's an animation of the 2 drums. Let's see if the MPEG will actually play. Let me pause this. Okay, I've downloaded a picture. I'll see if this will actually go through. I'll play it through several times. Okay. So if you look very carefully at the left here, these two drums, namely this and this, I mean, this actually looks like a tanagram. It's sort of a rearrangement of this. If you kind of put that up there and you put that on the side, and there's, I guess, some kind of group representation proof to why you have the same spectrum. But that was actually an unknown problem, whether those would have the same spectrum again. So that sort of concludes what I wanted to do today. And just getting back to the format for the final projects, what I'd like for you to do is to choose one of these 14 problems or offer up one that we haven't covered. And it should have a clear, concise statement of the problem, either in its original historical form or its current form, as much of a historical background as you can find on the web, and I've given you sort of starting points. And please don't just cut and paste huge amounts of stuff from other people's websites. I want you to sort of synthesize and write in your own words why this is an important problem. Also, investigate the areas of mathematics that have had some impact by people attempting to solve or succeeding in solving the problem. Summarize the key elements in the solution of the problem or attempts at the solution of a problem or proving a theorem, again in your own words. And then any kind of additional material, if you're familiar with Maple or MATLAB or C++, you'd like to write a program that would actually illustrate an algorithm or something, that's fine. Or you could, for problems that don't lend themselves to numerical, compile an extensive bibliography of references to that problem or visualizations of that problem or special cases or whatever. So what I want you to do is sort of become the leading expert in class on one of these 14 areas here. So just to reiterate, there's 10 problems in Lecture 19 and 4 problems in Lecture 20. You are allowed to work on this problem. I mean, more than one person can choose a problem, but I don't want you to work together. This should be individual effort. And try to submit it as electronically as you can, because I do want to capture the results in a website. So I don't really want to have scanned in documents that are handwritten for some poor student to read.